So to avoid any disappointment, so this talk will be not as casual as yesterday. So we're starting to do some serious work, yeah. And please ask questions, yeah, especially here the PhD students. They should ask questions if they don't know a concept or whatever. It will, because it will be complicated. Many things are coming together today. And so I will talk about equivariant cohomology. Equivariant cohomology. And totally real fields. And this is essentially about some work I did years ago together with Sascha Belenson and Andre Levin. And I explain that here because in a certain sense, good. So I explain this work here because in a certain sense, it is the easier case of what I have done with Johannes Sprang. And it gives you, as I think, the main ideas really without too many technicalities. Yeah. So let's do some motivation. So let's talk about Bernoulli polynomials. And I will present some way which may be quite unusual. So let's fix x some real number, but which is bigger than 0 but smaller or equal to 1. And let k be an integer bigger or equal to 1. And then we can define the Hurwitz zeta function. And that is as follows. It's zeta x s. This is the sum, n equals 1 up to infinity. And we sum over 1x plus n to the s. Yeah, that's a variant somehow of the Riemann zeta function. And you study this in connection with the Riemann zeta function a lot. And here, the point is what is known as, so this has an analytic continuation to the whole complex plane with some pole. And there's a functional equation. And with this functional equation, you can see that the values at minus this integer is equal to minus, you take the k plus first Bernoulli polynomial in x and divide by k plus 1. And the Bernoulli polynomial, this is defined by the following generating series. So bk plus 1 x defined by the generating series. Take z e to the zx divided by e to the z minus 1. And you develop this into a power series in z. And what you get is some polynomial coefficients in x. And these are called the Bernoulli polynomials. Okay, factorial, and this runs from k equals 0 to infinity. Okay, yeah, that's the Bernoulli polynomial. It's mentioned there. Okay, so we understand these zeta values, and here somehow there's some change with respect to yesterday. Yesterday we considered positive values here. They had this pi factor, and here the negative values, they are somehow rational polynomials in x, yeah? And that is maybe something you should keep a little bit in mind. So, but now if you study directly the functional equation, you get another expression for these values, and that will turn out to be important. So, and that's as follows. Minus k. I just give you the result. Some Fourier analysis which you have to do. And here you sum over all elements in the whole group Z in this lattice without 0. And you take e to the 2 pi I nx divided by 2 pi I n to the k plus 1. Yeah, it is a certain, it already looks like Fourier series. And now I want to present a somehow strange perspective maybe on this series. So we put this in a generating series. So consider generating series of these numbers. We add some formal variable, I mean, like here with the Bernoulli polynomials, yeah? and we write it here, f x z. This is just, we write first, I do what I really want. I want a generating series of these negative values of the over zeta function. So I take zeta x minus k, and then I take z to the k divided by k factorial here, this generating function. And now I rewrite it with this Fourier series as follows. So this is sum k bigger or equal to 0. And here I put the Fourier series in z without 0, e 2 pi I n x divided by 2 pi I n to the power k plus 1. Yeah. Yeah, there's some z missing here. Z to the k divided by k factorial. The k factorial goes away because the k factorial was there, sorry, in the functional equation. Yeah, so you have that series, and now this is somehow the generating series. Yes, say we want to say something about these values, that they are rational. We know this in this case, but in the general case we don't know it. So what could we do? The point is, we want to know, yeah, one idea could be to look at this generating series and see, can we characterize it in some sense uniquely, this generating series? And then from this unique characterization, can we get information about it? And what you observe is this satisfies some differential equation. So if you apply the following operators, you differentiate with respect to x minus, and then you take a z times dx, and you apply it to this f of xz, then what you get is the following. You get the sum over all z minus 0 of e to the 2 pi I x nx times dx. Yeah, easy calculation. And now, what is this? And now, if you're somehow are used to Fourier theory on the circle, then you recognize what that is. This is essentially, I mean, if we would add somehow 1 here for the 0, which is missing, then this is just the Fourier series of the delta distribution on the circle. Yeah. So what comes out here is you take the delta distribution at 1 minus dx. Yeah, that's the term which is missing on this side to make this an equality. So these are now, I consider this now as differential forms with distribution coefficients, yeah, which are called currents. As currents on the circle. Yeah. That's maybe a quite unusual point of view. And now, once you make this observation, you see maybe the geometry of the circle should play a role here. And if it plays a role, you want to play around with differential forms. You maybe have the idea you want to characterize this as a differential form with certain properties, yeah, with this delta function, but then you run into trouble that this differential form here, yeah, for this operator, it's not closed because there's always this dx coming up. And that makes a problem, and we want to have this dx going away. And this we do by smoothing this form in a certain sense a little bit. Currents are currents as on all manifolds. This means you take differential forms with distribution coefficients. Yeah, yeah, instead of C infinity functions as coefficients for differential forms, you take distributions. Distributions are linear forms on differential forms with compact support. Yeah, it's a dual space with certain topologies. This you have this generating series. I look at this differential equation and I get at this series. Yeah, this is a differential form somehow on the torus. You have problems with convergence already, but you realize if you know the theory of currents, this is really gives a current on the torus. Yeah, it's a differential form with a coefficient distribution, which is given by this series. And this series is known to be the Fourier expansion on the torus of the delta distribution at 1. Yeah, that's Fourier analysis. And I mean, here in Kanpur, there are many people doing PDE. They know this, of course, because this is related to fundamental solutions of differential equations. So, sorry? Exactly, and that's the reason why the dx, that's the reason why, so if you put the dx to the other side, then it's the identity you know, but this just means, okay, it's missing there, but we have the dx. I will remove the dx for you now, yeah, that's my next goal, and we do it as follows. We fix an auxiliary integer, which is bigger than 1, let's call it c, and we fix also a certain function on 1 over c divided by z to what shows s to z. Yeah. So observe this here. This is somehow the c torsion part, torsion of the circle. Yeah. These are the roots of unity on the circle. Yeah. And we will consider them as this. And the function does the following. So an element in here, say A, is mapped to either, so -1 if A is not 0, and to C -1 if A is 0. Okay, this we do. And now we consider a little bit modified series. Consider the alpha modified generating series. And this is simply defined as follows. So I take C of fxz minus the sum over A from 0 to C minus 1 from fx minus A divided by C comma Z. So what do I do here? I shift my function so simply by these torsion points, and I assign a weight to each shift. So if the shift is by A, then it gets the weight alpha of A in front, and you can write it like this. Okay, and then if you do this, you observe that the sum over all alpha of A, this is exactly 0, and you get the following differential equation of this modified generating series. And this is now just, you take the sum over A equals 0 to C minus 1. Alpha of A times delta of A over C minus the sum of alpha of A equals 0, C minus 1 times dx. And that here is 0, so the dx disappears. So what we get is, so we have a differential operator applied to the series, and we get a bunch of, this is all a bunch of delta functions at the torsion points on the circle. Yeah? So this means as a function on the circle, this satisfies outside the torsion points the differential equation that differential of this is 0. Yeah? So that's a geometric condition.
In this expression for alpha f, there is no alpha on the right hand side.
Here, yeah, the alpha, because I've chosen it in such a way, it goes away. You see, this is, so what I really write here is the sum A equals 0 to C minus 1, alpha of A, f of x minus AC, comma z, and if you put it in, then you get this. Yeah? Sorry, it was too fast. Yeah? Okay. So, let me maybe write down the idea and then explain the idea more in detail. The idea is now as follows. So, let A be any commutative ring, first of all. Commutative ring. So, for example, complex numbers. But that will be not the most important case for us. And then we want to do the following. We construct a local system of power series modules, power series in this auxiliary variable z. Yeah, these are all power series there. On the circle, on S1, such that the f alpha xz is a section satisfying some residue conditions. At the torsion points 1 over c, nobody can see, inside S1. So what does that all mean? I'm perfectly aware that usually the number theory students don't learn about local systems, which is a mistake. So So let me do a little recall here, or maybe mention for the first time. And I do it right away in the generality I need it later. So let L be a lattice of rank n. So this means it's just a free abelian group of rank n. And then I have fixed this A, and then AL, this is the group ring. Group ring of L. And that's not difficult to describe, and all the people who do Iwasawa theory here, they know how this works. That's just the ring of Laurent, finitely Laurent polynomials, yeah, in n variables. T1 inverse up to Tn inverse. So with respect to some basis of this lattice L. So that's just somehow like a polynomial ring, not so hard to understand. On the other hand, I learned that Tewari was a person interested in group rings, yeah. So that's very apt to have this in this lecture. So then let's consider M an AL module. So this means this is an A module, and M is an A module together with an action of L. And if I have such a thing, I want to do a local system, and now where I want to do it, so let V be L tensor R. This is an Rn vector space. And then let us consider TL. This is the torus where I divide V by the lattice. So that's isomorphic to n copies of the circle. Yeah? So that's a geometric situation. And from topology, you know that this is somehow the universal covering of that torus. And L is the fundamental group. So if you have a module for L, you can write down what is called a local system on the torus, and I give it to you explicitly. You do it as follows. So on V times M, L acts by L times V comma M equals V plus L Lm. Maybe for consistency, one should take minus, but that doesn't matter. So, and then I can simply quotient out this L action here. Quotient out the L action, and this I call M tilde. And that's now something which lives, obviously, over this torus TL. And that is what is called the local system. So associated to M. And to be even more concrete, let me say, so this is a locally constant sheaf. But you can describe it in this here very explicitly. And that's as follows. So if U is some open subset in the torus, open, then you have to say what are the sections of this bundle over U. And this you can write down. These are the functions S from the inverse image of that U. Yeah, remember we have here pi, which maps to this. So pi inverse image. That's something in here in V. Yeah, so if you think of the circle, you take a segment of the circle, then in R, you will have many, many disjoint segments mapping to this segment. Yeah, that are these images. And of course, the group here, L, so in the circle it would be Z, this somehow acts transitively on these things. Yeah, so you require, so the sections turn out to be just the following. So these are the maps here which satisfy the following. So if you take S of U plus L, it should be minus L times SU. And this is for all U in the inverse image and for all L in the group. You can write it down like this. So that's what is a local system. And but now there is even a very important case. When we go to the complex coefficients here, then we can consider the following. Then we consider the associated vector bundle, C infinity vector bundle. So we take the complex valued C infinity functions on TL and tensor this with this bundle over C. So this is a complex vector bundle on the torus of dimension n, and it is equipped with a differential with what is then called a connection on this vector bundle. So nabla, which is simply you take the usual differential tensor the identity map. So this goes from m tilde infinity to the differential C infinity differential forms on the torus tensor m tilde infinity. Yeah, that's a certain differential here. And so now after I have explained all this, I can say more about what the plan is here for us. So, so again, the idea, yeah, so find a local system of A power series Z modules on the circle S1 such that the differentiation, such that the associated delta is equal to the differential operator which we had before. Yeah, and then so I give it a name. This will be called log on S1, and then we want that somehow the F, this generating series modified by alpha, this becomes a section of this bundle on the torus without these torsion points with values in log. And then I have here the differential map, and yeah, and then I want to say this satisfies certain conditions here in this differential form, which I want to have here. This satisfies certain conditions in the torsion points, namely that if I extend it to the whole circle, then it becomes a current, which is exactly the delta distributions here. I will write that down later more precisely, but to understand how one computes this, I forgot something to mention here. I do that now. Namely, that you can compute somehow the group cohomology, the cohomology of these local systems by differential forms. That's very important. So sure. X0? There's no X. Yeah, this is plus a residue condition, which I'll make precise later. sorry. The condition is that I mean, will be a section here, in general, a differential form. And if you extend it somehow to these torsion points, it should be given by these delta distributions. Yeah. I will also explain why we would like to have that and what that means for this generating series. Yeah, first of all, I mean, it looks like we're doing really something completely silly. Yeah, we know about these values. We know that there are Bernoulli polynomials. We know explicitly somehow the generating series. Yeah, everything is there. But you see, this is true for this zeta function, but it is not clear how to do this in general for totally real fields. Yeah, so the problems start there. Yeah, so let's be content and see if we find a way which is maybe more complicated, but which gives us a lot of information at the same time. For example, what is missing in the other approach and is completely unclear is about the integrality property of Bernoulli polynomials. Yeah, so these coefficients, are they divisible by certain primes or not? Yeah, and this approach will all clear that up in one stroke. Yeah, and it will even do more. It will, this I will show in the last lecture, it will even give us a periodic L function interpolating these things. Everything in one stroke. Yeah, so it's worth the effort to work a little bit here. Okay, so what I wanted to say is that so you can compute, one can compute the cohomology of this local system by differential forms or even currents, yeah, differential forms, because if you simply write down the following complex, which you do also in the analysis of manifolds, so you go to the C infinity differential forms on the torus and take them all. So here's this whole complex. So maybe I write it a little bit more here. So M tilde, then you go to omega 1, C infinity, M tilde, and so on. Yeah, you'd always take this differential here. Then this is a fine resolution, really, of this sheaf M tilde. So this means the cohomology groups on the torus of M tilde can be really calculated somehow by the kernel of D on omega I C infinity tensor M tilde to Ci plus 1 M tilde divided by the image. Yeah, so as one learns in analysis class in the second year, analysis on manifolds, and that works here as well. So this we will use, and now the task is, of course, to find such a local system and to see what we want. But now let me, before we dive into this, because it will be technical, let's maybe have a short look at the situation of these L values for totally real fields, because there you will see that the situation is much more complicated in terms somehow of the generating series. So let's briefly look at totally real fields. And this is the case we want to attack, yeah? So, because here we don't have these nice series of Bernoulli polynomials and so on. what do we do? So we consider a finite field extension. So this is the degree of f over q is n, and f should be totally real field, totally real. All embeddings are real, and then we let OF be the integers here of that field, integers. And we fix two ideals, fix F and B, two ideals in this ring. And then it is known. So then we put L. Yeah, this is written on purpose. This will be the letters we will later use. We take F times B inverse. Yeah, that's a fractional ideal in F. And in fact, this is a free Z module of rank n. Yeah. And then we observe that 1, the element 1, which is in the field, F tensor R, divided by this L, that is an F torsion point. And this means it is in the kernel of the following map. So you take this real vector space, F tensor R. This is just an R to the n. Sorry? OF. Yeah, thanks. Thanks. So this is in the kernel. So we have here F times B inverse. And then this is a sublattice of F tensor R B inverse. And so we have a map here. And the kernel are the F torsion points. And 1 is in there. Okay. So now, what does one consider? What kind of zeta functions here for totally real fields come up? Yeah, in this Siegel-Klingen theorem, which I mentioned yesterday, I can write them down explicitly, and then we have a look. Please ask. I know it's now demanding. So you do something which is somehow a little bit similar to this Hurwitz zeta functions. You define this, and this is, you take the sum over all elements F plus F in B inverse, and here I have to be a little bit technical, which are totally positive. Yeah. Totally positive. And you divide by the totally positive 1 units modulo F. Modulo F. And the sum is then just, you sum over all lambdas in here, and you take 1 over the norm of lambda to the S. Yeah, that's zeta function which comes up. More classically, these are written as follows. You have the ray class functions for the ray class of B, and they are defined as follows. So this is the sum over all integral ideals in the ray class defined by B, and A has to be co-prime to F, and so that is integral, and then you do 1 over norm A to the power S. And that's some of the ray class, the partial zeta function for the ray class B modulo F. the relation between these two is very easy. This is just the following. This is a norm e to the minus s times zeta of 1 fb inverse s. I'm just giving this now for the number theory experts so that they see we treat the usual things here. Yeah. What is now interesting, so in the case of the Hurwitz zeta function, we looked at the functional equation. Let us do this here, because there is one difference which we will see immediately and which causes a lot of pain. So the functional equation reads here as follows. So for k, we have the functional equation. Yeah, so even if you don't understand that, you can see now the functional equation, similar things coming up as before, and not s, minus k, sorry. So this is k factorial now to the power n. Yeah, we're not scared for this. Then there's norm of f, norm of b inverse coming up. There is the discriminant of f, square root of this coming up. All this is not frightening. Yeah, that's okay. For number theories, that's usual that you have this bunch of integers. But now the sum, that's something we have to look carefully. So now this is over all linear forms on the lattice we are talking about here, FB inverse, yeah, without zero. This is the dual lattice. Linear forms on z to the n, on this group. And, but that's not all. We have to divide still by this group of units. And then, if we do that, it looks perfectly similar to what we had before. So we take the norm of 2 pi I mu to the power k plus 1 again. Yeah? So we would like to have a generating series for these values as well. And now if you think, okay, the approach we wanted to do for the Bernoulli polynomials, yeah, it didn't convince you so far because there were easier approaches. And now you get even more in trouble if you look at this. Because here, you see immediately, I mean, if you want to interpret this as a Fourier series, you're in trouble, because here you divide by the units. Yeah? If the units were not there, then this is a Fourier series essentially on the torus, TL, and then you could differentiate and you get something with this delta distribution there and so on. So this means somehow there is not such an easy approach with this differential equation anymore. Somehow these units have to come in as well. Yeah, and this we have to study now and to get a solution. And in fact, the approach I already started to outline, this will guide us here, and we will see that everything falls in place very naturally once we go through the technicalities. Sure. Mu is a linear form on this lattice, and we extend it to f, and then we apply it to 1. Yeah? Okay. Okay. So now we come back to the local system, and I'm afraid I have to talk a little bit about this local system, and this will be a little bit technical, so, or more technical even, if you like. I think it should be paragraph 3, is this true? Logarithm. sheaf. And so let L be this lattice as before, yeah, rank n, and A is also this ring, commutative ring, and we have the group ring AL, group ring. But and now it turns out that the group ring is not so good, because in fact what we want is something like a power series ring, and that's not a power series ring. And there's now a trick which, I mean, somehow, yeah, it's very hard to motivate why you should do it, but there are very good motivations to do this. That's really an observation of Bailenson connected with his earlier work, that what one has to do here is the following. So then we consider the following completion of the group ring. Namely, we take the inverse limit over the augmentation ideals of the group ring, yeah, j k plus 1. And j is the kernel of the augmentation of the group ring to A. Yeah. So this is generated by symbols L minus 0 here in the group ring. And I take this completion, yeah, this is a completion of this ring. Yeah, so I point out for all the Selma group and Iwasawa students here that you have seen something like that. Yeah. Suppose A is ZP, yeah, and L is just the lattice, then this is the Iwasawa algebra in n variables. Yeah. So that's not so bad from this perspective to consider, but it will also be very important that we have this completion later. So, and then we form on this L, we have now an action of L itself. I mean, the group acts on the group ring, yeah, in a natural way, but even more is true. Any group which acts by linear automorphisms on L also acts on the group ring. So let gamma be a subgroup of the automorphisms of L, linear, Z-linear automorphisms. Yeah, can think of a group of matrices here with integer coefficients, and then gamma, of course, on AL, and you see that it also, because it preserves the augmentation ideal here, obviously, it acts also on this completion. Yeah, and so later we will consider simply the following. As I said, L will be F times B inverse, and gamma, this will be just the units. So gamma acts on that, and L also acts on that. That's clear. Yeah, L acts on L prime by simply shifting L prime plus L, and so this is in fact AL becomes a semi-direct product action of gamma and L. Now, module. And in particular, it's an L module, so we can define a local system, which is called log, associated to this module. This is now a local system on the torus TL, yeah, which was V divided by L, and V was L tensor R. It's a purely topological situation. We forget about everything, no number fields here, whatever. Yeah, we do a little bit funny Fourier analysis on this torus, but we do it equivariantly for this gamma. And this equivariance for gamma, that's really extremely important. And that also gives the name to this talk because we will consider gamma equivariant cohomology. Okay. This is gamma. This is an arithmetic subgroup. Yeah, I mean, if I choose a basis, this is GLNZ. Yeah. Okay. More questions? Please ask. Otherwise, it might be too late because it goes on like that. Yeah? So the gradient is quite steep here. So, okay. So we have to understand that local system a little bit. So first of all, I mean, this is somehow associated to the representation of the fundamental group of the torus. Fundamental group of the torus at the point, yeah, I never know how to call it. It should be 0 maybe, the image of 0 in TL. That's, of course, really canonically identical to L. And so what we get is that the stalk of that sheaf, that's canonically isomorphic to the thing we started with. So how should you think about such a thing? So for example, on the circle, this is really something like a fiber bundle, and in each fiber over the torus, you have somehow something which is non-canonically isomorphic to this ring. Yeah, whatever that ring is. Maybe I can also say it. So this is non-canonically isomorphic to a power series ring in n variables. Yeah, T1 up to Tn. Yeah, power series ring. That's good. Yeah, that's something we wanted to have. The non-canonically, that's bad because we want to keep track of the gamma action, and that is not possible like that. But that will be another issue. Okay, so this is pi. This is pi 1. This is a fundamental group. Sorry. Thank you. That's the fundamental group of the torus. Okay. And so now, because that is non-canonical, we need another map to a power series ring. And we have to be very careful with these algebraic questions. I don't want to get too deeply into this, but because this will give some nice connections later to Iwasawa theory, I mentioned this in any case. So there's always a canonical map. In fact, we have a canonical map without choosing any basis of this completed group ring to the completed symmetric tensor algebra. So this is, you take the symmetric tensors in LA and you complete it with respect to the augmentation ideal. So that's just product K bigger or equal to 0 to infinity of the tensor symmetric powers of L to the A. And for those who have never seen this before, I mean, the symmetric powers you might have seen, the tensor symmetric powers are not the same if the coefficients are not rational or characteristic 0. And for integrality questions, it's really very important to to differentiate between these things. And this map I call the moment map because of some relation with Iwasawa algebras later. And I can give it very explicitly. So some of these generators L here, they simply go to the exponential series L tensor K, and L K runs from 0 to infinity. And why do I call this the exponential series? Because this here, this is in fact, in this algebra, the kth power divided by kth factorial. Yeah, so in the tensor algebra. Okay, that's some kind of exponential map you always have. And then we need another fact, and that's the following. We need that if we consider a torsion point in this torus, VL, so let's say it's an N torsion point, So N is an integer bigger than 1. Yeah, so that just means X is in N inverse L, modulo L. Yeah, and then there exists, so and, that's very important. This N is invertible in our ring. Yeah, so N invertible in A. Then we have a canonical isomorphism of the stalk of this logarithm sheaf in X, again with this group, completed group ring. So in 0, we always have it. And for torsion points, we have it whenever the torsion order is invertible in A. And this little extra condition, which seems strange and harmless at the moment, it will later imply that the integrality of these zeta values, which we get from this approach, they will always have this, they will be not completely integral, but you always have to allow some denominators. Okay, now I know questions. Please ask, because otherwise I go on to cohomology and then everybody is lost. Ask now, last time. X upper star, so that's the stalk of this. This is the stalk at X of that sheaf. Yeah. More questions? So now we have to go through this cohomology, and then I explain you the strategy again. And then I want to convince you how one can get strong results about these values. What was non-canonical? This one or this one? This is now canonical, yeah, but it was canonical for 0 as well. For 0, it was natural. By definition, is somehow trivial. Here, it is that it is canonical. So you see, what is the fiber of this local system really? Log. If you write it down, this is not a group ring, but it is somehow. I mean, I write it on purpose a little bit vague. So this is somehow. You take the same construction, but on the lattice shifted by X. This is now not a group anymore, yeah? But it is a coset of the group, yeah? And this coset, this is somehow, this has a simple transitive action of this group, but it is not a group itself. And to make it a group, like with affine space, you need to change a 0 point, choose a 0 point, yeah? So this you cannot do here, yeah, because the x is not in L. But if you multiply this by n, then you get into NL, which is a group again, and you can talk about the group lattice. And if n is invertible in A, then you can also, so you get to this ring. And if n is invertible in A, you can get also back. And this gives you this isomorphism. Yeah, yeah, it's unfortunately technical. Yeah. So. You will see it now. Yeah. So the point is, if you calculate, you go to C coefficients and you calculate the connection of this, it will be exactly the connection we have seen in the beginning. Yeah. That will be something. I can do it for you, but all in order. Yeah. Okay. So okay. We have that thing. Or maybe I do it actually now. So because you asked, so aside, let's see if A is C, that what is the connection here on this local system? Yeah. So this map in general is not an isomorphism, but if A is a Q algebra, it is an isomorphism. So so if A is C, then we have CL is isomorphic to this completed tensor symmetric powers. L tensor C, this vector space. So this is like a power series ring if you choose variables. And now the point is that the associated logarithm sheaf with the C coefficient, if you extend the coefficients to C infinity, you go to this vector bundle. I mean, as I write it, it doesn't make too much sense. It's an infinite dimensional vector bundle. You have to be a little bit careful here. I don't go into this. That vector bundle, this has now a trivialization. Yes, this has a non-zero global section on TL, and that is just the section you send V on the torus to the exponential function of V. Yeah. So really now the exponential series. V considered as an element there, tensor K, V tensor K divided by K equal 1 to infinity K factorial. And you can see that if you write, I mean, if you choose a basis here, how shall I call it? Z1 up to Zn basis of L tensor C, then this V can be written as V1, Z1 plus and so on, Vn, Zn. And the V1, Vn, these are somehow functions, C infinity functions in terms of this point on the torus, and the Z1 up to Zn, these are the variables here. And in this way, you get really a C infinity map from the torus to this bundle, and this trivializes it. And now you can calculate the connection with this. So there is an isomorphism. Let me write it the right way. So there's an isomorphism now of the trivial bundle. So a CL with C infinity section. This is with trivial L action. And the connection here is D minus DZJ tensor, the variables Zj sum over J, and 1 up to N. This local system is via this section isomorphic to the logarithm sheaf C infinity with its given connection. And this will be exactly the operator which I should write the V. Maybe this is the VJs here. Yeah, the coordinates. So that's exactly the differential operator which showed up in the generating series for the Bernoulli numbers in the case n equals 1. And if you trivialize that bundle, you get exactly trivial coefficients with this differential operator. Yeah, and you see it by differentiating just this section here, and then you get via this expression you get exactly this differential form showing up. Okay. Sorry for this. So this means with all this effort, we have constructed a bundle with a nice differential operator, which has the right shape. And now we have to construct somehow the classes, and we want to construct them without knowing anything about values of zeta functions and generating series and so on. And we want to construct them also for arbitrary rings A. Yeah? Over C, this might have this differential operator, but over any other integers, we don't know. And to do this, we have to do some cohomological construction. So we have the following theorem. So we look now at the cohomology of that local system. And what is known also that this is isomorphic. So maybe this appeals more to some people in the audience. So I mentioned this. This is the same as the group cohomology of this AL module. Yeah? If you would have here the group ring, then this cohomology is known. This is then a co-induced module, and you know that this is 0 except in degree n. In any case, this is a free abelian group, so the group cohomology here can be easily calculated. And you can also do this with differential form. In any case, the result is exactly that this is the same as if there were here just the group ring. and you get, this is 0 if I is not n. And this is isomorphic to NHN of TL just with A coefficients if I is equal to n. And this is non-canonically isomorphic just to A. So this is somehow, this group ring is as difficult as possible, so it avoids a lot of cohomology classes here, and that is good. Yeah? Have you seen this group cohomology somewhere? Group cohomology? No. Then you compute it by differential forms, but then it's a little bit more difficult to see how that this is really 0. I don't go into the proof. I think it's easy, but I think I don't want to stretch today too much. Otherwise, the next lecture is completely empty, which I would like to avoid. So, with this result, we can now do the following. Yeah, this in a certain sense, it does say that this local system is as complicated as possible. Yeah, so it doesn't have much cohomology. It will make so the reason why we need it is because it gives us now a uniqueness condition on the generating series. So somehow on the class we want to see get which then becomes the generating series. Yeah. So that's the purpose of that. So what you do is now the following. We consider this torus. And now in this torus, we have these C torsion points, which are now denoted by like this. So this is C inverse L modulo L. Yeah. And I want to consider, now cohomology classes in the complement of this. Yeah. So remember, for n equals 1, for n equals 1, we had something which was a section in S1 minus the C torsion points with values in this power series ring. I mean, it was also the logarithm sheaf, in fact, logarithm sheaf. This was this generating series. This was a section here because it satisfied this differential equation z dx. And this means it was a global section here by this equivalence between global sections of this local system and things which satisfy this differential equation if I go to C infinity here. Yeah. So, but I can erase this again because this exactly means it is a global section over C. Yeah. So in general, we want to have cohomology classes here. And now there is the localization sequence in cohomology. Sequence, which gives you the following sequence. So you get here h n minus 1 of the torus with values in log, goes to the h n minus 1 here. And by the theorem above, that's just 0. And the next step, it goes to the cohomology with support in these C torsion points on TL with values in log. And then it goes on to Hn of this, which is just this. So we have that little piece. And you see the classes in here, yeah, this is some group. And the classes in here, they are uniquely determined by the properties they have here. And this one can compute, this is just the global sections of things supported on the C torsion points with values in this module L. So if C is invertible in A, then one can compute that. So, question? Because what is happening here, I want to explain in the case n equals 0. So for n equals 0, we have the following. So we have sections S1, and here we have the torsion points. We take them out, have logarithm sheaf, and then we go here. In fact, we would go to H1 with support in these torsion sections on S1, but this can be calculated to be just somehow this is just a direct sum over all these torsion points with values in this AZ. There's a question? N equals 1. Thanks. N equals 1. Sorry, but this means invertible elements. This means support. Support in these torsion points. Yeah. So that here, this is something like a residue map, and what is now true that if you compute the cohomology not in terms of differential forms but in terms of currents, then this map goes as follows. So you have a differential form here. This is just a zero form. Yeah, it's just a function. And then you extend the function to the whole circle, but then it's no longer a differential form. You can extend it only as a current, as a distribution. Yeah, and then you evaluate, you look what is the distribution in these points. I mean, you cannot evaluate usually a distribution, but the map here goes really to the residue of this distribution, yeah, which measures the difference between taking the distribution associated to a C infinity function and then differentiate, or first differentiate and then taking the distribution associated to this function, yeah, which is not the same if the function has singularities somewhere. And so this is really goes, this maps, this is exactly this condition which we had before. So the fxz alpha, which is a section in here, this satisfies really that via this residue map, it goes exactly to the following function in here. So it goes to this alpha, which associates, alpha is in here. So alpha we consider as a function on this torsion points as before, yeah, to A now. And it maps as before. The D in here goes to -1 if D is non-zero, and to C -1 if D is 0. Yeah, so and now what what this gives us is that the section here, yeah, is uniquely determined just by this residue condition. So differentiating it and then seeing what kind of delta distributions you get here in these torsion points. And this makes it unique, and it makes it unique also over any other ring which is contained in C. Yeah. So the computation works in C with C infinity coefficients. But the point is we have the following diagram. So let's now consider the simplest case. So we invert just this C in the integers. Yeah, we allow denominators by C. And then this is contained in the complex numbers, of course. And we have a diagram which is as follows. So we consider now these sections without the, let me here also denote this torsion section. I give it a name. Big D, with values in the logarithm sheaf, say with this ring Z1 over C. And then we can extend the coefficients minus the log complex numbers. And so we can go here, we make this residue map to the direct sum over the D in D of the Z inverse Z, Z completed. And here we can also extend coefficients, D and D, now complex coefficients. And we have the residue map here. And by naturality of all this construction, it is clear that this diagram commutes. This means if I start with a class which is defined for this ring with these integrality conditions, yeah, and I go here and then to there, it's the same as going to here and then to there. So if I want to compute how this class looks like, I can do this over the complex numbers, but then I know just from my construction that the coefficients of the power series I get have to be in this ring. Yeah. So that's extremely strong. Yeah. So this means out of this we get immediately the following result. D was this, did I erase it? It was the torsion points here, sorry. D is this is these torsion points in the circle, yeah? Sorry. Which term is not always equal? This is not always equal because it injects into here. I mean, it is, you can exactly say what it is because it injects always in here and you have elements in here. Yeah? Each element you choose here will be hit by this. Yeah, so if I choose this alpha, which is a map here, yeah, this is certainly something in there. Yeah, this is the family which associates to D alpha of D. That's in here. I get some section which maps to this. Okay? Yeah, I have some of the alpha is here, and then I get a class which is usually called the topological polylogarithm pol alpha, which maps to this. Yeah, and that is unique because the map is injective. Yeah, and I only have to say. So why is it hit? The only condition I have is that it maps to 0 here, and this condition exactly means that the sum of the alpha D is 0. Yeah, that means that it is mapped to 0 here. Yeah? Okay. I deviated so much from my notes that say this all in order. Let me just state the result now for, in the case n equals 1, because my time is running up. And so then what we see from this is that the if we look now again at that generating series Fz, and you compute it in terms of the Hurwitz zeta function, you get the following. You get C times zeta x minus k minus C to the minus k zeta C of times x comma minus k, and then z to the k divided by k factorial. And the result is that these coefficients, so this implies, so this construction implies that these are now all coefficients here. Yeah, and so you have produced an extremely strong integrality statement without using any particular properties of these totally real fields or something. Yeah, this is just something where you speak about cohomology classes complicated, yeah. And I understand if you have not too much exposure to cohomology, all this is lost on you. But maybe you can see here, the idea is you characterize a certain class by this residue condition uniquely. And then if you can do this for any ring, for each ring for which you can do it, you get that the coefficients of the result are actually in that ring. Yeah, and that is extremely strong because it produces the known integrality results for the Hurwitz zeta function, but it produces also the known integrality results for the totally real fields, which were obtained by completely different methods by Deligne and Ribbett. Very complicated because they had to study really integral models of Hilbert modular surfaces and so on. Yeah, also not an easy theory. And here, in a certain sense, this is quite elementary to do this. Yeah, and we get it on the nose. And I will explain on Friday also that you get also the P-Adegau function interpolating these values on the nose here. Yeah, maybe you see it already how it will work, but that's it. Sorry, the lecture was now a little bit confusing. This is because I felt that somehow my audience was a little bit overwhelmed by all these technicalities. I didn't prepare this maybe too well. So thanks anyhow. You can make it show up. Yeah, that's so at the moment I have a thesis which clarifies the connections explicitly. But you see, I didn't explain now so much the gamma equivariant part here. Yeah, but so Shintani, as you know, is needed if you want to decompose the lattice exactly by the unit action. Yeah. And so this means you want to avoid this annoyance that the series is somehow divided by lattice divided by gamma. Yeah. So this means you write this somehow, you decompose this into certain cones, and then this is a finite sum of things over cones. Yeah. Cones 1 plus cone R or something. Yeah, that's Shintani's method, and this is a substitute for the gamma equivariance of this thing. So in a certain sense, if you compute the gamma equivariant cohomology, then you can see it if you go, you do it like Banai and all these people have done for the Shintani co-cycle. They write it also in this equivariant way. And the point is you go to somehow to the algebraic torus, and then the Shintani decomposition gives you somehow an affine covering. And this affine covering, if you calculate the cohomology with respect to this is the same as computing the equivariant cohomology there. Yeah, and you can make that explicit here, but it is, in a certain sense, it is not so obvious, the relation. Yeah, but you can see it by choosing somehow the right affine coverings for this algebraic torus, which underlies this.
You don't need any.
Never. I mean, which also means, of course, if you now ask a question like, okay, what comes out of the Shintani method is that you can write the L value as a linear combination of certain Bernoulli numbers. That you don't see here. Yeah, that's not so clear. It's not so clear to me if one could recover that. Yeah. This, this is Julius' thesis. Yeah.
So again, I saw like some. Sorry to make a comparison again, but like some similarities with how Harder constructs Einstein cohomology, and then. So I was wondering if.
No.
Some kind of map.
No. There's no. I mean, there is the different. I mean. It's exactly the point. I mean, Harder can never get integrality results. And he can never, I mean, he has even a hard time just to prove rationality results. Yeah. And the point is as follows. His construction is completely transcendental. So he uses somehow the Eisenstein summation to produce classes. And then he has to check that there is some, there come up some certain. So you have to evaluate the Eisenstein class in the center of functional equation. You have to check that they really are close there. Yeah, and this gives a certain condition which is not always fulfilled, and you have to work hard that you get it. Yeah, but the construction is you take an infinite sum. So you lose all control about integrality, rationality, and everything. This is this construction which only works really if you are in C infinity coefficients, C infinity functions, something like that. Yeah. Here the construction is completely topological. You see, the C infinity coefficients, this was only motivation. Yeah. I mean, I could have started just saying, okay, I take a lattice, I make this group ring, I look at the cohomology, that's something well defined, and I don't care how this is computed. I can write this thing down without ever mentioning a series, whatever. Yeah, this is just the cohomology class which is uniquely determined. Full stop. Yeah. Of course, this is only interesting if you know how it looks like, and then you have to compute it. But because it is constructed for arbitrary coefficients, yeah, you don't have to worry really how this is later computed. Yeah. You can compute it with the method you like. Yeah. But you know, right, that from the construction, the coefficients in the series you get in the end, they will be in the ring you started with. Yeah?
This is the information that
yeah, it is somehow, it is not a purely cohomological topological construction. Yeah. Other further questions? So all the students should come now, and then I explain more because they look so frightened. So,
You can have a longer chat outside.
yeah, sure. Thanks.
Thank you.